Hello everyone, Assalamualaikum warahmatullahi wabarakatuh and good day to every one of you. Welcome to my video. So basically this is a lecture video for subject Electrical Circuits 1 code BEV10303 and in this video we are going to continue our discussion for chapter 4 which is circuit theorems. Okay, so what are the topics that we are going to cover in this video is basically the last subtopic of the chapter, which is a subtopic 4.4, which is the maximum power transfer theorem. Okay, so basically this is the last video for chapter 4. Okay, and what is the maximum power transfer theorem actually, and why do we need the maximum power transfer theorem? So we are going to see in details in this video. So in practical, when we design a circuit, okay, so we design that circuit so that it can be able to deliver the power to the load. So it is desirable to maximize the power that can be delivered to the load. Alright, so the Thevenin equivalent circuit that we learned in the previous subtopic, it can be used in order to find the maximum power that a linear circuit can deliver to the load. Okay. So, in order to understand on the topics of maximum power transfer, so we consider the following circuit, right? So this is basically the equivalent Thevenin circuit where you have a V supply, which is the V Thevenin, connected to the R Thevenin in series, okay? And then the equivalent Thevenin circuit is connected to the RL. Okay, so this is your R load. Okay, so now you need to find the power that absorbed by this load. Okay, so the power is equivalent to I squared R. Okay, in this case, I is equal to, okay, you can just apply your voltage divider rule here. So I will be equal to V Thevenin divided by R Thevenin plus RL, okay, squared multiplied with RL. Okay, so this is the equation of the power that absorbed by the resistive load. Okay. Next, based on the equivalent Thevenin circuit, we know that the V Thevenin and then the R Thevenin is fixed. So the only that change is the RL. So by varying the RL, the power delivered to the load varies as per sketch in graph. Okay, so as per this graph, you can see that the power vary. Okay, depends on the value of RL. Right. So by looking to the graph, we know that the power is small for the small value of RL, okay, and then the power is also small for the large value of RL, okay, and then the power is maximum for some value when your RL is between 0 and infinite. Okay, so you don't know what is the value here. So according to the maximum power transfer theorem, the power is maximum when your RL is equal to R Thevenin. Okay, so how do we need to prove this? Okay, so we can just refer to the next slide. All right, so we know that based on the graph, the power is maximum when dP over dRL is equal to 0. Okay, where P is given by this equation. Okay, so you just differentiate P over RL in order to find the power maximum. So based on this equation, the V Thevenin squared, we can bring it to the outside. Okay, we can factorize it and then we just differentiate RL divided by R Thevenin plus RL squared. Okay, so how to differentiate this? You can actually apply the quotient rule. Okay, so here you can consider as U and here is you can consider as a V. Okay. And then you can just use the formula V du over dx minus U dV over dx divided by V squared. Okay. So in this case, first of all, V is R Thevenin plus RL squared multiply with du over dx. So you differentiate RL over RL, you get 1. Okay. Minus U is RL multiply with dV over dx. So in this case, you differentiate R Thevenin plus RL squared, differentiate over RL, and then you get 2 multiply with R Thevenin plus RL divided by V squared. Okay, so this is a V squared. Alright. And then after that, we can further simplify this equation so that we have here and here, I can cancel out R Thevenin plus RL squared. So here got R Thevenin plus RL to the power of 4. So I cancel this, become R Thevenin plus RL divided by R Thevenin plus RL the power of 3. Okay, so here and here also can be cancelled, so it leaves with minus 2RL. Alright, so the power is maximum when dP over dRL is equal to 0. So this whole thing can be considered equal to 0 in order to find the power maximum. Okay, and then after that, the V Thevenin squared will bring to this side become 0. So R Thevenin plus RL to the power of 3 will bring to this side become 0 as well. So finally, you have R Thevenin plus RL minus 2RL equal to 0. Okay, and then you can further simplify here. RL minus 2RL become negative RL, and then finally R Thevenin will be equal to RL. Okay, so it is proven that the maximum power is transferred to the load when your RL is equal to your R Thevenin. Okay, so this is what been said by the maximum power transfer theorem. Okay, all right. And then the maximum power, according to the definition of the maximum power transfer theorem, so it states that the maximum power is transferred to the load when the load resistance, which is RL, is equal to the Thevenin resistance, which is R Thevenin. So in this case, RL equal to R Thevenin. Okay, so when your RL is equal to R Thevenin, your power that absorbed by the load is the maximum. Okay. Alright, and then how to find the maximum power transferred? Okay, it's basically we can just use back the equation of P that we have in the previous slide. You know that your P is equal to V Thevenin divided by R Thevenin plus RL squared multiplied with RL. Okay, so this is the equation of power absorbed by the load. And then after that, you can just substitute the value of RL equal to RTH, because you know when the RL is equal to RTH, the power is maximum. Okay, so P max will be equal to V Thevenin squared divided by R Thevenin plus R Thevenin, because RL will be equal to R Thevenin multiply with R Thevenin. Okay, RL will be equal to R Thevenin. Okay, and then based on this, we can further simplify our equation. So finally, we have V Thevenin squared divided by 4 RTH. Okay, all right, because 2 RTH squared become 4 RTH squared. So RTH squared, you can cancel with this RTH. So that's why here you just have 4 RTH. Okay, so this is basically the equation that you can use in order to find what is the maximum power transfer obtained by the load. Alright, okay. Okay, so next let's have a look at the following example 4.10 on how to apply the maximum power transfer theorem. Okay, so based on the question, you need to find the value of RL for maximum power transfer in the following circuit. Okay, so it means that now you need to find what is the value of RL that you need to adjust in order to find the maximum power transfer to be happen in the circuit. Alright, so according to the maximum power transfer theorem, you know that your RL must be equal to R Thevenin in order to maximize the power transfer from the source to the load. Okay, and then after that, we need to find the maximum power transfer. So meaning that here you need to find what is the P max when the RL is equal to R Thevenin. Okay, so the solution for this example, basically you need to find the equivalent Thevenin circuit first. Okay, so the step number 1, first of all, we need to remove your RL, and then you can just turn off your independent source. Okay, and then after that, you need to find the R Thevenin, which is the R equivalent from the terminal AB. Okay, so just now based on the previous slide, here you have a voltage source. Again, here also you have a voltage source, but you turn off both of the voltage sources. So that's why here you have a short circuit. Okay, and then just now you have RL here, and then you just remove your RL. And then this circuit is basically you can redraw it to become here. Okay, so you have a 5 ohm in parallel with 3 ohm. Okay, so what is the R equivalent at this point? Okay, basically is equal to 5 ohm parallel with 3 ohm. So 5 multiplied with 3 divided by 5 plus 3 equal to 1.875 ohm. Okay, so in this case, R Thevenin is equal to here, and then you know that based on the maximum power transfer theorem, the maximum power transfer happen when your RL is equal to 1.875. Okay, RL is equal to R Thevenin. Okay, and then after this, we need to find the Thevenin. So step number 2 is a find Thevenin from the terminal AB. So basically this is your circuit. You just put back your independent source, and then we remove the RL, okay, and then the V open circuit is equal to the Thevenin. Okay, so now we need to find the value of Thevenin. So basically we can apply the mesh analysis. So by applying the KVL around the loop, you get this equation. Right, so based on this equation, because here become open circuit, so you can consider you have a I mesh current here around the loop. Okay, and then after that, before you can apply your KVL, you need to assign the polarity for each of the element based on the mesh current. So here you have positive, negative, positive, and negative. Okay, from this point you see a negative terminal. So negative 50 plus voltage across 5 ohm is equal to 5I plus 3I plus 25 equal to 0. Okay, alright, and then based on this, you can further simplify your equation. So negative 50 plus 25 become negative 25. 5I plus 3I become 8I. So finally, I will be equal to 25 divided by 8. So I will be equal to 3.125. And then after that, we can apply the KVL around the small loop here, or we can call it as an inner loop. So here you have negative 50 plus 5I plus Thevenin equal to 0. Okay, so you know I is equal to 3.125. You can just substitute the value of I. So finally, Thevenin is equal to 34.375 volt. Okay, so this is your Thevenin. Next, you need to draw your equivalent circuit. So your Thevenin equivalent circuit is given by here, where you have a Thevenin, V supply is Thevenin connected to the R Thevenin, which is 1.875 ohm, and then you just put back your RL. Okay, so now you need to find the P max when your P max for the circuit. Okay, so calculate P max absorbed by the load. So you know that your equation of P is given by this equation, right? And then you know that P max happen when RL is equal to R Thevenin. So this is said by the maximum power transfer theorem. So P max is equal to, you can just substitute the value of RL is equal to R Thevenin. So in this case, Thevenin is 34.375 divided by R Thevenin plus R Thevenin. Okay, so R Thevenin is 1.875. Multiply with RL is equal to R Thevenin multiply with 1.875. Okay, so you can just use your calculator to get the value of P max. So finally, P max is equal to 158 watt. Okay, or you can just use the formula that we learned in the previous slide, where the P max is equal to V Thevenin squared divided by 4 RTH. Okay, you can just simply derive from the equation, or you can memorize the formula. Okay, so based on the formula, you get the same answer, which is 158 watt. Alright, so that's all on the topics of maximum power transfer theorem. So thank you for your time. Thank you for watching my video. Bye.